In this video, I'm going to talk about Rolle's theorem. Rolle's theorem has the following assumptions. Let's say f is a function that has three properties, okay? So property number one is continuous on a closed interval a comma b. Two is differentiable on open interval a b. And three, f of a is equal to f of b. If these three conditions are satisfied, then there is a c, some number c, in the open interval ab such that f prime of c is equal to 0. So f is a function, right? F is a function. It has the following properties. It's continuous on the closed interval, differentiable on the open interval AB, and at boundary points, the values are the same. F of A is equal to F of B. And if these three conditions are satisfied, then there is a point C that is in the open interval AB such that f prime of c is equal to 0. I'm going to show you how to prove this theorem, but by considering three different scenarios. So let's consider scenario number one, or case one. Okay, so in a simple scenario, think you have a function that's between a and b, and it's constant. Okay, it's a horizontal line. In that case, obviously this theorem holds true. Why? The function, this constant function, is continuous, right? Is differentiable, and also f of a is the same as f of b. All these three conditions are satisfied, given conditions 1, 2, and 3. Then, of course, this is a constant function. It looks something like this. F of x is equal to c, and we know that f prime of x is going to be 0. So, in essence, this is not only true for one point in between a and b, but true for every single point in between a and b. But the theorem says that there exists. So all we need is just one point. It could be more, no problem. But theorem says that there exists a point c such that f prime of c is equal to 0. In this particular example that I gave you, here we have infinitely many points which will give me the derivative value to be 0. Now, let's go ahead and consider case 2. So, let's say this is my point A, this is my point B, and the function moves something like this. I just made it up. Okay, so point A, f of A, and point B and f of B. Remember, according to the assumption, f of A is equal to f of B. This is very important to remember. Now, if you start at point A, what could happen? So let's say you start at point A. You could either go up or down. If you go straight up, it's a constant function if you keep going continuously that way straight. However, let's assume that there is a point in between a and b. There is a point x in between a and b such that f of x is greater than f of a. And of course, we are going to consider the other scenario too. So let's consider the situation where f of x is greater than f of a. If that is the case, then by extreme value theorem, between A and B, there must be a maximum. Just a reminder of the extreme value theorem. If you have a function that is continuous on a closed interval, then it achieves a maximum and a minimum in the open interval AB. Okay, so in our case, the function obviously is given to be continuous on the closed interval. Therefore, there must be a maximum. So let's say that maximum happens somewhere, right? We can call it C, somewhere in between A and B. Now, Fermat's theorem tells us that if there is a maximum somewhere, it's a local maximum, then the derivative at that point, f prime of C, must be equal to 0. Once again, extreme value theorem ensures that there is a maximum point between A and B because of the continuity of the function in the closed interval AB. Now, Fermat's theorem, so we find an extreme value or maximum value. So let's say that point is at C somewhere, right? Now, Fermat's theorem tells you that, okay, this C must be a local maximum at least, right? If it's an absolute maximum, it has to be a local maximum as well. So by Fermat's theorem, since this is a local max, f prime of C must be 0. So we just showed that there exists a C such that f prime of C is equal to 0. Now let's consider case 3. Okay. Here what I'm gonna do, so this is my A, f of A, and this is my B and f of B. Here I'm gonna do something like this. You can make it any shape you want. So in this case, last time we assumed that f of x is greater than f of A. Now this time we are going to assume that there is a point x in between A and B in the open interval AB such that f of x is less than f of A. Then again, by extreme value theorem, there must be an absolute minimum because the function f is continuous on closed interval AB. Therefore, there must be a minimum as well, absolute minimum somewhere between A and B, right? Open interval. Now, again, we can say that that point is C somewhere, okay, between A and B, all right? So now, C is an absolute minimum in the open interval, then it must be a local minimum as well, right? Then we can use the Fermat's theorem that ensures that by using Fermat's theorem, it assures that f prime of C is equal to 0. So in this case, also we found a value C in the open interval AB such that f prime of C is equal to 0. Now, if we look at all three cases, by the way, that's all it can happen. If f of A and f of B are equal, that means they have the same value at the same height or same y values, then there are literally three things can happen. The simplest case is that you go straight from f of A to f of B. That's one thing. That's a horizontal line. Even though my line doesn't look horizontal, but it's a horizontal line. Now, the other two options are, there is a value of f of x which is going to be less than f of A, or a value for f of x which is going to be greater than f of A. So that's all it can happen, right? So f of x could be always f of A, f of x could be greater than f of A, and f of x could be less than f of A. These are all three possibilities. Nothing else could happen. And we have covered all all these scenarios. In each of these scenarios, we have shown that there is a point C in between such that f prime of C is equal to 0. Again, there is a point C in between A and B in the open interval A and B such that f prime of C is equal to 0 for all three cases. So that pretty much concludes the proof of the Rolle's theorem. This is an important theorem. It has applications in many areas. And also we use this theorem to prove the mean value theorem, which we will be proving. I hope that this discussion was helpful. Thank you very much.